There was a time when the Earth had no forests, no mountains, and no familiar horizon. More than 4 billion years ago, our planet was still young. Its sky was not blue, but a dense canopy of carbon dioxide and water vapor. Stable continents did not yet exist, and much of the crust was thin, fragile, and still cooling beneath an ocean that was repeatedly thrown into chaos. Then the impacts came, not the kind that ended the age of the dinosaurs, but objects many times larger. Asteroids up to 100 kilometers, which is about 62 miles across, struck this planet again and again over tens of millions of years, releasing enough energy to melt rock, reshape the crust, and erase entire oceans in moments. Scientists call this chapter the Late Heavy Bombardment. The largest impacts were powerful enough to vaporize Earth's oceans, wrapping the planet in superheated steam before the water slowly condensed and fell back as rain. Yet almost none of the evidence survived. Over billions of years, Earth's own geology buried, melted, and recycled nearly every scar, forcing scientists to reconstruct this story by studying the cratered surface of the moon instead. Then came an even stranger discovery: tiny zircon crystals from Western Australia, each smaller than a grain of sand, revealed that liquid water already existed during this violent era. One crystal, approximately 4.1 billion years old, may even preserve the chemical signature of life itself. If that evidence is correct, then life did not appear after Earth's first apocalypse. It survived through it. Even more remarkably, many of the same asteroids and comets responsible for this destruction were also carrying water, organic molecules, and some of the fundamental ingredients required for biology. The bombardment that threatened to erase our planet may also have helped prepare it for everything that followed. So, in tonight's journey, we're traveling back in time to uncover the extraordinary story of Earth's first apocalypse, how our planet endured one of the most violent periods in its entire history, and why every living thing alive today may owe its existence to whatever managed to survive the fire. Picture the earliest chapter of the solar system as a broad, rotating cloud of gas and fine dust circling a newborn sun. Around 4.6 billion years ago, nothing resembling the orderly arrangement of planets existed. Every future world began as scattered particles moving through this glowing disk. Tiny grains met and adhered, becoming pebbles. Pebbles gathered into boulders. Boulders merged into planetesimals, the building blocks of planets. Through a process known as accretion, each collision added another layer to worlds that were still taking shape. Growth depended on repeated impacts, making collision the ordinary rhythm of creation from the very beginning. Far beyond the growing rocky planets, the giant worlds occupied a layout unlike the one familiar today. Jupiter, Saturn, Uranus, and Neptune traveled in a much tighter arrangement, circling between roughly 5.5 and 17 astronomical units from the Sun. An astronomical unit is the average distance between Earth and the Sun, approximately 150 million kilometers, which is about 93 million miles. Outside their paths stretched the primordial Kuiper Belt, a crowded collection of icy bodies containing an estimated 30 times the mass of Earth. Compared with the sparse population found there today, this distant region held an extraordinary abundance of frozen material awaiting its own destiny. For hundreds of millions of years, this arrangement changed very little. The giant planets continued their steady paths, while the icy belt retained its dense population. Closer to the Sun, the inner planets continued gathering material left from the birth of the solar system. Although collisions remained common, they gradually became less chaotic as available debris declined. Across this long interval, The architecture of the young planetary family appeared balanced, even while subtle gravitational influences continued shaping every orbit. Earth emerged within this restless environment around 4.54 billion years ago. Soon afterward, around 4.5 billion years ago, a body about the size of Mars struck the young planet. That tremendous collision produced the material that eventually formed the Moon, while leaving Earth's exterior covered by a global ocean of molten rock extending thousands of kilometers deep. That is nearly 1,864 miles. The surface glowed with intense heat, and no familiar landscape had yet appeared. As countless years passed, that molten exterior gradually released its heat into space. Around 4.4 billion years ago, the first durable crust began forming across portions of the planet. Rainwater eventually collected in low regions, creating the earliest liquid water known to have existed on Earth. Evidence for this turning point survives inside microscopic zircon crystals discovered at Jack Hills in Western Australia. These durable minerals formed while magma cooled, preserving chemical signatures that reveal interaction with liquid water at the surface during an age once imagined as entirely inhospitable. This emerging world remained youthful and incomplete. Its crust was still developing, its oceans were only beginning to gather, and its atmosphere continued evolving through volcanic activity. Even so, the ingredients associated with future habitability were already appearing together. Water covered portions of the surface, solid ground continued expanding, and geological processes steadily transformed the planet into a place capable of sustaining far more than bare rock. This fragile balance formed the foundation upon which everything that followed would unfold, establishing the stage before the solar system entered one of the most destructive chapters in its long history. Balance can persist for immense stretches of time, even within a system shaped by gravity. The early solar system seemed to have settled into such an arrangement, with each giant planet tracing its path, while countless smaller bodies circled beyond them. Beneath that appearance of stability, however, every orbit was exchanging tiny amounts of momentum with the surrounding disk of debris. Those subtle changes accumulated across millions of years until they altered the entire architecture of the planetary family. The explanation favored by many planetary scientists is known as the NICE model, developed in 2005 by Alessandro Morbidelli, Rodney Gomes, Clementis Tsiganis, Harold Levison, and colleagues. The model takes its name from the French city where the research was carried out. According to this idea, Jupiter and Saturn drifted outward little by little as they exchanged gravitational energy with countless smaller objects orbiting nearby. Their migration unfolded at a pace that would have been impossible to notice in any ordinary lifetime, although gravity never stopped keeping its patient account. Eventually, the two giant planets entered a configuration called a 2-to-1 mean motion resonance. In this gravitational relationship, Jupiter completed exactly two journeys around the Sun during the same interval that Saturn completed one. Each repeated alignment strengthened their combined gravitational influence, much like a steady rhythm reinforcing itself. Every return to the same positions added another small disturbance, allowing the effect to build until the orderly paths of both planets became increasingly unstable. Their orbits gradually stretched from nearly circular paths into elongated ellipses that carried them through regions they had not previously occupied. These changing trajectories altered the balance throughout the outer solar system. Gravity passed the disturbance from one world to another, and the consequences spread far beyond the original pair. Uranus and Neptune responded to this growing instability by moving outward, eventually reaching the distant regions where they continue to travel today. As those massive planets shifted across space, They crossed the dense population of icy bodies filling the primordial Kuiper Belt. This region still contained material equal to roughly 30 Earth masses, providing an enormous supply of frozen objects waiting for gravitational encounters. Every close passage scattered more of these icy worlds onto fresh paths. Some were hurled completely out of the solar system, while many others began long inward journeys toward the warmer planetary region surrounding the Sun. The disturbance reached the asteroid belt as well. Along its inner boundary existed an early population of rocky objects, often called the E belt, occupying the region between roughly 1.7 and 2.1 astronomical units from the Sun. An astronomical unit is the average distance between Earth and the Sun, approximately 150 million kilometers, which is about 93 million miles. Once the giant planets disrupted the gravitational balance, many members of this inner asteroid population also escaped their original orbits and joined the growing stream of incoming projectiles. Across the solar system, millions of icy and rocky bodies that had once occupied predictable paths became wandering impactors. Gravity transformed an orderly arrangement into a prolonged cascade of collisions, delivering the greatest sustained wave of asteroids and comets the inner planets had experienced since their earliest formation. The change unfolded through natural orbital physics, with each interaction adding another thread to a chain of events that reshaped every rocky world circling the young sun. Once the planetary orbits released their store of wandering debris, the inner solar system entered an era measured by collisions of astonishing size. The objects approaching Earth bore little resemblance to the small meteorites that occasionally streak across today's sky. Many were immense asteroids and icy comets, stretching for tens of kilometers, which is about several to many miles across. They carried enough mass and velocity to transform entire regions of a planet within moments, leaving scars that dwarfed anything produced during the more familiar chapters of Earth's later history. The impactor that ended the age of the dinosaurs measured about 10 kilometers across, which is about 6.2 miles, and its collision reshaped the course of biological evolution. During the Late Heavy Bombardment, many incoming bodies were thought to match that scale, while others exceeded it dramatically. Some may have measured 50 kilometers, which is about 31 miles across. A few models even allow for objects approaching 100 kilometers, which is about 62 miles, placing them among the largest impactors believed to have struck the young Earth after the planet itself had formed. Every increase in size multiplied the energy released at impact far beyond a simple doubling. Computer simulations provide a sense of the enormous totals involved. Some estimates suggest that Earth received nearly 100 impactors capable of excavating craters more than 1,000 kilometers wide. That is nearly 621 miles. A crater of that size would stretch across a region larger than many modern nations. Each event excavated tremendous volumes of rock, launched debris high above the atmosphere, and redistributed material across great distances. These were not isolated catastrophes separated from one another by geological ages. They formed part of a prolonged interval during which destructive encounters remained an expected feature of the young solar system. The rhythm of those impacts differed greatly from any human sense of time. Millions of years might pass between the largest collisions, allowing landscapes to cool and change before another enormous object arrived. Smaller impactors continued to strike more frequently throughout the same era, adding countless additional craters between the rare giants. On the scale of planetary history, this produced a sustained barrage extending across tens of millions of years, even though individual impacts remained widely separated within a single lifetime measured by geology. Earth was far from alone in receiving this punishment. Mercury, Venus, the Moon, and Mars occupied the same inner region of the solar system and experienced the same flood of incoming bodies. Their differing sizes and geological histories shaped how each world preserved the record, although the bombardment itself reached them all. Scientists compare crater populations across these neighboring worlds to reconstruct the intensity of that shared episode, especially where surfaces have survived with fewer later changes. Mercury still displays an extraordinary abundance of large craters, while the elevated southern highlands of Mars preserve another extensive archive of ancient impacts. These independent records agree with one another despite forming on different planets under different conditions. Together, they reveal that the bombardment reached across the entire inner solar system, leaving a common signature written into multiple worlds at once. Earth occupied the center of that same celestial storm, even if the evidence on its own surface has long since faded from view. Every collision left behind more than a crater. It rewrote the landscape from the point of impact outward, releasing an amount of energy that surpassed ordinary imagination. A single large asteroid carried the force of millions of nuclear warheads delivered within a single millisecond. In that instant, rock behaved less like solid ground and more like liquid, responding to pressures and temperatures rarely experienced anywhere else on the planet. Across the Hadean Earth, each major impact became a geological event capable of changing the face of an entire hemisphere. The largest impacts liquefied the upper portion of Earth's crust almost immediately. Layers extending 1 kilometer deep, which is about 0.62 miles, or even farther in some regions, melted into broad sheets of glowing rock. Those pools spread across hundreds of kilometers, which is about many hundreds of miles, before cooling into fresh crust. Mountains that might have begun forming disappeared into molten stone, while fractures opened deep below the surface. The crust became a shifting mosaic, repeatedly broken apart and rebuilt as fresh impacts interrupted every stage of recovery. Powerful shock waves traveled downward through the crust and into the mantle. Those waves compressed rock with extraordinary force before allowing it to rebound, disturbing regions far beyond the original collision site. The movement altered stresses already present inside the young planet, encouraging volcanic activity across surrounding areas. Fresh magma found pathways upward through weakened crust, adding widespread eruptions to landscapes already transformed by impact. Fire from below joined destruction arriving from above, blending two geological processes into one continuous episode. Material blasted upward during these immense collisions filled the atmosphere with pulverized rock, vapor, and molten droplets. As those droplets cooled while falling back toward the surface, they solidified into tiny rounded beads known as spherules, small spheres of rapidly cooled impact melt. Layers containing these microscopic beads remain preserved within rocks dating to around 3.47 billion years ago, offering one of the surviving records of impacts that shaped the early Earth. Their presence allows scientists to recognize events whose larger scars have long since vanished. The greatest collisions carried another consequence that reached beyond stone. Oceans exposed to these impacts could be converted into enormous volumes of superheated steam. Water that had collected across the surface entered the atmosphere, surrounding the planet with a dense envelope of vapor. Surface temperatures near the impact site exceeded 2,000 degrees Celsius or 3,632 degrees Fahrenheit, while conditions across much of the planet remained lethally hot for extended periods. Only after substantial cooling could water condense once more and return as rain, gradually rebuilding oceans that had briefly ceased to exist in liquid form. Recovery unfolded between the largest impacts, although it rarely lasted forever. Fresh crust hardened, rainfall restored bodies of water, and atmospheric conditions began shifting toward greater stability. Then another incoming object crossed Earth's path and erased much of that progress. The sequence repeated across millions of years, with intervals of rebuilding interrupted by renewed devastation. Instead of a single catastrophe, the bombardment became a recurring transformation, repeatedly renewing the surface until almost every trace of its earliest landscapes had been replaced by newer ground shaped through fire, impact, cooling, and persistent geological change. Air leaves no fossil cliffs or mountain ranges. Its history survives through the effects it leaves behind, revealing itself in minerals, chemical signatures, and the behavior of the planet that carried it. During the late heavy bombardment, Earth's atmosphere became far more than the blanket surrounding the surface. It stood directly in the path of incoming worlds, absorbing consequences that reached far beyond the impact sites themselves. Every major collision reshaped not only land and water, but also the invisible envelope that made the young planet different from the empty space beyond it. When a large asteroid or comet struck at tremendous speed, the force of the collision generated expanding shock waves that raced upward as well as downward. Part of that energy accelerated atmospheric gases until some exceeded Earth's escape velocity, allowing them to drift permanently into space. Planetary scientists describe this process as impact erosion, the removal of atmospheric gases by an impact energetic enough to launch them beyond the planet's gravitational reach. Instead of remaining wrapped around Earth, portions of the atmosphere escaped into the darkness between planets, reducing the protective layer that had taken immense spans of time to accumulate. The atmosphere of the early Hadean differed greatly from the one surrounding Earth today. It contained abundant water vapor, carbon dioxide, methane, ammonia, and nitrogen released through vigorous volcanic activity. This mixture continued evolving as the planet cooled, making it especially vulnerable during an age when atmospheric stability had not yet been established. Every large collision disturbed that balance once again. Material blasted skyward carried gases away, while heated rock and expanding vapor altered pressure and composition across the globe. Atmospheric change became another recurring consequence of planetary impacts, unfolding alongside the reshaping of oceans and crust. Recovery depended largely upon the planet's interior. Volcanoes released fresh gases through eruptions and widespread volcanic vents, gradually rebuilding what impacts had removed. Carbon dioxide, water vapor, nitrogen, and other compounds slowly returned to the atmosphere through this persistent outgassing. That renewal unfolded across millions of years, making it far slower than the near instantaneous atmospheric losses caused by the largest impacts. Earth repeatedly found itself restoring an atmosphere that could again be diminished by another incoming object before the rebuilding process had fully finished. These alternating episodes of loss and renewal influenced nearly every condition at the surface. Atmospheric pressure changed, temperatures shifted, and the chemical environment surrounding young oceans evolved again and again. Such variations affected how efficiently heat remained trapped near the ground and how rapidly water cycled between vapor and liquid. Compared with modern Earth, the environment remained exceptionally unstable, shaped by repeated interruptions instead of long periods of uninterrupted equilibrium. Some scientific models suggest that the earliest atmosphere may have possessed a pressure exceeding 27 times that of the modern world because of its dense carbon dioxide content. Such a massive gaseous envelope helped retain heat, allowing liquid water to exist even while the young sun emitted less energy than it does today. Without that insulating effect, surface water would have struggled to remain stable under those early conditions. Across the bombardment, Earth's atmosphere became a structure under constant reconstruction. Rock, water, and air evolved together, each responding to impacts in different ways while remaining connected through the same planetary cycle. Long before the atmosphere resembled the one sustaining life today, it endured repeated destruction and renewal, gradually acquiring the resilience that later generations of living organisms would inherit. The oldest witness to this chapter of Earth's history never stood upon Earth at all. It circles above the planet each night, carrying a surface that has remained largely unchanged across billions of years. While Earth's restless geology continued reshaping continents, recycling crust, and renewing landscapes, the moon preserved a different kind of memory. Its face became a record that endured, allowing scientists to examine events that our own world could no longer display. Earth is remarkably efficient at erasing its past. Plate tectonics carries ancient crust into the mantle, where it melts and is recycled into new rock. Wind, water, volcanic eruptions, and countless other geological processes steadily modify whatever survives at the surface. Across immense spans of time, mountains disappear, oceans shift, and continents transform. Because of this continual renewal, no known crustal rocks, older than approximately 4.3 billion years, remain exposed on Earth's surface. The physical evidence of the bombardment itself has almost entirely vanished, leaving only scattered mineral clues instead of complete landscapes. The moon followed a very different path. After its early history, geological activity declined dramatically. It developed no system of moving crustal plates, experienced almost no erosion, and lacked flowing water capable of wearing away impact scars. Craters that formed billions of years ago largely remained where they first appeared. Each collision added another mark without removing the older ones beneath it. The lunar surface therefore became a natural archive, preserving a sequence of impacts that Earth itself could no longer retain. Across the pale highlands of the moon, this history is written in extraordinary detail. These bright, rugged regions formed approximately 4.3 to 4 billion years ago and remain densely covered by overlapping craters of every size. Even without telescopes, many of these ancient highlands can be distinguished from Earth as brighter portions of the lunar surface. Every crater contributes another page to a geological record stretching back toward the earliest chapters of the inner solar system, allowing scientists to reconstruct an era otherwise hidden from direct observation. Among the most striking features are the enormous impact basins scattered across the lunar surface. Mare Imbrium, Mare Serenitatis, and Mare Nectaris stand among the greatest scars produced during the bombardment. Mare Imbrium alone measures roughly 1,250 kilometers across, which is about 777 miles. Its immense size exceeds the width of many nations and illustrates the scale of the objects striking the moon during that period. Similar basins reveal repeated encounters with impactors large enough to reshape broad regions of an entire world. The darker areas filling many of these basins tell another part of the story. These broad plains, known collectively as the Maria, are not impact craters themselves. After the giant collisions, excavated enormous depressions, molten rock later rose from the lunar interior and spread across the basin floors. As those lava flows cooled and hardened, they created the smooth, darker surfaces that contrast so clearly with the brighter surrounding highlands. Together, they give the moon its familiar two-toned appearance when viewed from Earth. By studying crater densities, basin ages, and samples returned from the lunar surface, scientists assembled the first compelling evidence that the inner solar system experienced an intense period of bombardment between roughly 4.1 and 3.8 billion years ago. The moon became Earth's enduring geological companion, preserving the history that our living planet could no longer keep for itself. The evidence that transformed this story did not emerge from a telescope or a computer simulation. It arrived inside carefully sealed containers carried home by astronauts returning from another world. Between 1969 and 1972, the Apollo program placed human beings on the moon 6 times. Those expeditions returned approximately 382 kilograms of lunar rocks and soil. That is nearly 842 pounds. Every sample carried a fragment of the moon's deep past, preserved with remarkable fidelity across billions of years. The later landing sites were selected with exceptional care. Apollo 15, Apollo 16, and Apollo 17 touched down close to three of the moon's immense impact basins, Imbrium, Nectarus, and Serenitatis. These locations were chosen because scientists hoped to recover rocks that had formed during the colossal impacts themselves. Rather than collecting ordinary surface material alone, the mission sought geological evidence created at the precise moments when those enormous basins first appeared. Among the most valuable discoveries were pieces of impact melt rock. This type of rock forms when the extraordinary heat and pressure generated by a massive collision melt existing material almost instantly. As the molten material cools and solidifies, it creates entirely new rock whose internal structure records the moment of its formation. Unlike older rocks that may preserve a complicated history of heating and alteration, impact melt rock begins its geological record anew at the instant the collision ends. That property made these samples especially valuable for radiometric dating. Many contained radioactive isotopes that behaved like natural clocks. When a large impact melted the original rock, those clocks effectively restarted from the beginning. Scientists measured this timing through a technique called argon 40, argon 39 radiometric dating. The method determines how much radioactive potassium 40 has gradually changed into argon 40 since the rock last experienced complete melting. Because the transformation proceeds at a known rate, researchers could calculate the age of the impact responsible for creating each sample with impressive precision. Laboratories studying rocks collected from different Apollo missions soon noticed an unexpected pattern. Samples gathered from widely separated landing sites, representing different impact basins and different parts of the lunar surface, repeatedly produced ages clustering between roughly 4.1 and 3.8 billion years ago. The agreement proved striking. Independent rocks, collected hundreds or even thousands of kilometers apart, that is nearly many hundreds of miles, appeared to record major impacts occurring within the same relatively narrow span of geological time. In 1974, scientists Fuad Terra, Dmitry Papanastasiou, and Gerald Wasserberg published an influential analysis describing this concentration of impact ages. They proposed that the moon had experienced what they called a terminal lunar cataclysm, a period during which an unusually large number of giant impacts occurred over a comparatively brief interval. That interpretation provided the first strong physical evidence suggesting the inner solar system had passed through an exceptional episode of bombardment instead of a steady decline in collisions after planetary formation. The implications extended far beyond the moon. Earth possesses a stronger gravitational pull and presents a larger target to incoming objects than its smaller companion. If the lunar surface recorded such an intense concentration of giant impacts, the young Earth almost certainly endured an even greater number. Although its active geology erased the visible scars, the samples carried home by the Apollo astronauts revealed a chapter of Earth's earliest history that had survived intact on the neighboring world circling above it. The oldest surviving pieces of Earth can rest unnoticed upon a fingertip. They are neither towering cliffs nor weathered mountains, but microscopic crystals that endured every transformation the planet imposed upon them. While the moon preserves the broad record of bombardment across its exposed surface, Earth's own testimony survives within these tiny minerals, each carrying a chemical memory from an age when almost every larger trace of the young world disappeared. These remarkable minerals are known as zircon, a crystalline form of zirconium silicate distinguished by extraordinary durability. Zircon forms within cooling magma, locking tiny amounts of surrounding elements into its crystal structure as it grows. Once formed, it resists melting, chemical alteration, and mechanical wear far better than most other minerals. Even after billions of years of burial, erosion, mountain building, and recycling through the crust, many zircon crystals retain the chemical signatures established at the instant of their crystallization, allowing scientists to reconstruct conditions that no longer exist anywhere on Earth's surface. One of the richest collections of these ancient crystals comes from the Jack Hills region of Western Australia. The rocks exposed there are much younger than the crystals they contain, yet they preserve an invaluable archive. Long ago, older rocks weathered apart, releasing individual zircon grains that rivers transported into accumulating sediments. These detached grains are known as detrital zircon crystals, meaning they were eroded from their original host rocks before becoming incorporated into younger sedimentary deposits. Protected within those sediments, many survived while their original parent rocks vanished completely. Among these crystals lies the oldest confirmed fragment of Earth ever discovered. One zircon from Jack Hills has been dated to approximately 4.404 billion years ago, with an uncertainty of plus or minus 8 million years. That age places its formation astonishingly close to Earth's earliest history, long before any intact crust from the same period survived. The crystal, therefore, serves as a direct physical connection to a world otherwise lost beneath billions of years of geological change. Its chemistry carries another remarkable message. Scientists measured the proportions of oxygen isotopes trapped within the crystal and concluded that the magma from which it formed had interacted with liquid water near Earth's surface before crystallization. This evidence suggests that oceans or substantial bodies of liquid water already existed approximately 4.4 billion years ago. The finding transformed scientific understanding by indicating that Earth's surface cooled enough to sustain water much earlier than once believed, well before the main phase of planetary bombardment reached its greatest intensity. Another zircon, dated to approximately 4.1 billion years ago, contains tiny inclusions of carbon whose isotopic composition has attracted considerable attention. Some researchers interpret those signatures as potentially biogenic, meaning produced by living organisms rather than chemical processes alone. Others urge caution, noting that alternative explanations remain possible. Even so, the discovery raises the intriguing possibility that life, or at least the earliest biological activity, may already have existed before the bombardment reached its proposed peak. Each crystal is smaller than a grain of sand, yet together they preserve an astonishing account of Earth's beginning. Their resilience allowed them to outlast continents, oceans, and countless generations of rock. Within structures almost unimaginably small, they reveal a planet capable of supporting liquid water during one of the most turbulent chapters in solar system history, preserving a memory that endured when nearly everything else was erased. Scientific ideas rarely remain unchanged once new evidence begins to accumulate. The proposal of a dramatic late heavy bombardment quickly became one of the leading explanations for the scars preserved across the moon, and for many years it was widely accepted as the best description of events. According to that interpretation, impact rates rose sharply around 3.9 billion years ago, after a comparatively calmer interval, producing a brief but extraordinary surge of giant collisions throughout the inner solar system. As additional lunar samples, improved analytical techniques, and new computer models became available, researchers began examining that picture more closely. The central question shifted from whether the bombardment had occurred to whether it truly took the form of a sudden spike concentrated within a narrow span of time. Gradually, scientists identified several reasons to reconsider the original interpretation without dismissing the evidence gathered during the Apollo missions. One concern involved the geography of the samples themselves. Although the Apollo expeditions returned an invaluable collection of lunar material, every landing took place within a relatively limited region on the moon's near side. Altogether, those sites represented only about 4% of the lunar surface. Such a small sampling area naturally raised the possibility that the collected rocks might not fully represent the history of the entire moon. A conclusion extending across the inner solar system therefore depended upon evidence gathered from only a small fraction of one neighboring world. Among those emphasizing this limitation was researcher Tom Harrison. He argued that any reconstruction of planetary history should carefully consider the statistical strength of its supporting observations. If most available samples originated from closely related regions, patterns appearing within those rocks might reflect local geological circumstances instead of a truly global event. His criticism encouraged researchers to broaden the available evidence before treating the proposed impact spike as firmly established. Another opportunity arrived through lunar meteorites. These rocks were excavated from random locations across the moon by later impacts before eventually traveling through space and falling to Earth, where many were recovered from Antarctica. Because their origins spanned a much wider range of lunar terrain, they provided an independent collection unaffected by the limited geography of the Apollo landing sites. When scientists measured the ages of impact melt within many of these meteorites, the results appeared more widely distributed through time, instead of gathering tightly around 3.9 billion years ago. Further analysis deepened the discussion. In 2016, researchers Banke and Tom Harrison published a study in the Proceedings of the National Academy of Sciences exploring whether the apparent concentration of ages might arise through the behavior of radioactive argon inside impact melt rocks. Their models suggested that diffusion of argon over immense spans of time could produce an age pattern resembling a narrow cluster, even without requiring a distinct planetary cataclysm. The familiar peak in impact ages, therefore, might emerge naturally from the dating process itself under certain conditions. Scientists associated with the Lunar and Planetary Institute proposed another possibility. They suggested that material ejected during formation of the enormous Imbrium Basin may have spread across wide portions of the lunar surface, if rocks from that single impact reached several Apollo landing sites. Samples collected from different locations could all preserve the age of one exceptionally large collision instead of recording numerous unrelated basin-forming events. The debate, therefore, evolved from disagreement over evidence to a deeper effort to understand exactly what the moon's enduring record was truly preserving. Another interpretation follows a different rhythm. Instead of imagining a brief surge that interrupted a calmer age, some researchers picture the young solar system gradually settling after its turbulent birth. In this view, there was no single moment when impacts suddenly became overwhelming again. The violence slowly diminished as countless fragments left over from planetary formation were steadily removed, leaving behind a quieter neighborhood through the passage of hundreds of millions of years. Scientists refer to this explanation as the accretion tail hypothesis. According to this model, the formation of the planets produced an enormous excess of rocky and icy debris that continued traveling through the inner solar system long after the major worlds had assembled. With each passing age, part of that material fell into the sun, part escaped the sun's gravitational influence altogether, and part collided with planets, moons, and smaller bodies. The overall number of impacts therefore declined gradually instead of rising sharply during a single interval around 3.9 billion years ago. Within this framework, the concentration of ages found in many Apollo samples reflects the nature of the preserved evidence rather than the true pattern of impacts. Every exceptionally large collision disturbed the surrounding landscape, excavating older rocks and covering broad regions with newly formed material. As those younger deposits accumulated, earlier geological records became increasingly difficult to recognize. The surface effectively rewrote portions of its own history each time another major impact occurred. Planetary scientists describe part of this continual reshaping as impact gardening. This process occurs when repeated impacts of many sizes churn, excavate, and overturn the surface through immense spans of time. New craters overlap older ones, ejecta blankets bury previous deposits, and fragments from fresh collisions become mixed with existing material. Gradually, evidence of ancient events is blurred or erased altogether. Under this interpretation, younger impact signatures naturally become easier to identify than much older ones, even if the bombardment steadily declined instead of occurring in one dramatic pulse. This alternative carries important consequences for the story of early Earth. Without a distinct planetary catastrophe centered near 3.9 billion years ago, intervals suitable for stable surface conditions may have lasted much longer than previously imagined. Oceans could have persisted across broader stretches of time. Geological processes may have continued with fewer interruptions, and environments favorable for increasingly complex chemistry might have remained available despite the continuing arrival of impactors. The early Earth would still have been an active and hazardous world, although its history becomes one of prolonged adjustment instead of repeated global resets, concentrated within a comparatively narrow window. Several observations from Earth's oldest surviving materials fit comfortably within this possibility. Zircon crystals indicate that liquid water existed very early in planetary history, while other geological evidence suggests that crustal recycling and perhaps the earliest forms of plate tectonic activity had already begun. Carbon preserved within certain ancient zircons has also encouraged discussion about biological activity before 3.9 billion years ago, although that interpretation remains under careful examination. The discussion continues without a final verdict. Even the National Aeronautics and Space Administration recognizes that a decisive answer may depend upon future lunar expeditions returning samples from many more regions across the moon. Each newly explored landscape offers another opportunity to refine the chronology of impacts and reveal whether the earliest chapters of Earth's history unfolded through a sudden catastrophe or a long and gradual fading of primordial chaos. A different possibility reaches even farther into the past, shifting the greatest turmoil closer to the birth of the planets themselves. This interpretation neither rejects the existence of a major bombardment nor accepts the familiar timing proposed by the traditional model. Instead, it suggests that the most intense period of impacts unfolded hundreds of millions of years earlier, during an era when the young Earth was still taking shape. This idea emerged through research led by Stephen Mogesis and colleagues at the University of Colorado. Their investigation turned away from the moon and examined another survivor from the earliest solar system. The focus became meteorites that originated from the asteroid Vesta, a large rocky body within the inner asteroid belt. Because Vesta formed in the same broad region as the terrestrial planets, it experienced many of the same large-scale events that influenced Earth during its infancy, preserving another valuable record of ancient collisions. The researchers examined impact melt preserved within these meteorites. Like comparable rocks collected from the moon, these samples formed when powerful impacts generated enough heat to melt existing material before it cooled and solidified once again. Careful radiometric dating revealed a pattern that differed from the familiar Apollo chronology. Instead of clustering around 3.9 billion years ago, many melting events grouped near approximately 4.48 billion years ago, pointing toward a much earlier period of especially intense bombardment. If that chronology proves correct, the consequences are substantial. The peak of the asteroid storm would shift by roughly 600 million years, placing the greatest concentration of giant impacts at a time when Earth itself was only about 80 million years old. During such an early stage, the planet remained far from the stable environment suggested by later zircon evidence. Large portions of the surface were still evolving, and long-lasting oceans may not yet have become established. The harshest interval would therefore belong to a chapter preceding the conditions associated with Earth's oldest surviving mineral record. This revised sequence also offers a straightforward way to reconcile observations that have sometimes appeared difficult to combine. Geological evidence indicating liquid water at approximately 4.4 billion years ago and possible traces of biological activity by approximately 4.1 billion years ago would no longer overlap with the most destructive bombardment. By the time stable bodies of water spread across the surface and the earliest environments favorable to life emerged, the greatest wave of impacts could already have passed into history, leaving Earth an opportunity to continue cooling and evolving. The proposal also carries implications for the broader architecture of the solar system. Models describing the migration of Jupiter and Saturn suggest that changes in their orbits destabilized reservoirs of smaller bodies, sending many toward the inner planets. Under this revised interpretation, that episode of planetary instability, including the crossing of their 2-to-1 orbital resonance, may have occurred considerably earlier than many previous calculations indicated. The same physical mechanism remains, although its place within the solar system's timeline moves closer to the beginning. This interpretation continues to represent a minority position among planetary scientists, yet it has attracted increasing attention as additional evidence accumulates. Its greatest contribution may lie beyond any single date, reminding researchers that Earth's first billion years remain one of science's least complete histories. Each newly analyzed crystal, meteorite, and lunar sample carries another fragment of that distant record, gradually refining a story whose earliest pages are still being assembled. Across the face of the moon, every crater belongs to a history that remains almost entirely intact. New discoveries have refined the chronology of those impacts, and competing models continue to reshape their timing, yet the landscape itself preserves one conclusion with remarkable consistency. The lunar surface records collisions of extraordinary scale, events unlike anything experienced during the most recent half-billion years of Earth's history. Whatever sequence ultimately proves correct, the evidence for immense violence remains unmistakable. Modern spacecraft have transformed that evidence from distant observation into detailed geological maps. In 2009, the National Aeronautics and Space Administration launched the Lunar Reconnaissance Orbiter to examine the Moon with unprecedented clarity. Orbiting only a short distance above the surface, the spacecraft photographed valleys, crater walls, lava plains, and fractured highlands at resolutions reaching approximately 1/2 meter, which is about 2 feet. Features once appearing as blurred markings from Earth became individual boulders, layered ejecta deposits, and intricate fracture systems extending across the ancient terrain. Those images revealed the staggering abundance of impact structures spread across nearly every region. Scientists have identified more than 300 impact basins measuring over 100 kilometers across, which is about 62 miles. Each basin represents an impact vastly larger than ordinary craters, excavating enormous volumes of crust and permanently reshaping the Moon. Their overlapping relationships preserve a complex geological archive that reaches back toward the earliest history of the inner solar system. Among them stands the South Pole, Aitken Basin, the largest confirmed impact structure known anywhere in the solar system. Stretching approximately 2,500 kilometers across, that is nearly 1,553 miles. It occupies a substantial portion of the Moon's far side. Its floor descends roughly 8 kilometers below the surrounding terrain, which is about 5 miles. The collision responsible released an almost unimaginable quantity of energy, penetrating deeply enough to expose material originating far beneath the original crust. A second mission expanded this picture by examining the Moon from an entirely different perspective. In 2011, the Gravity Recovery and Interior Laboratory mission launched two spacecraft that orbited together while measuring subtle variations in the Moon's gravitational field. Tiny changes in the distance separating the pair revealed differences in the density of rocks hidden beneath the surface, producing the most detailed gravitational map ever assembled for another planetary body. Those measurements showed that the lunar highlands had been fractured to astonishing depths. Instead of forming one continuous block of intact crust, vast regions resembled an immense accumulation of broken material created through repeated giant impacts. Damage extended tens of kilometers downward, indicating that ancient collisions altered the Moon far below the visible surface. The mission also identified numerous mascons, meaning mass concentrations, beneath many of the largest basins. These dense regions formed as crust was catastrophically removed during basin-forming impacts, allowing deeper mantle material to rise and contribute to the Moon's internal structure. Every one of these discoveries carries meaning for Earth as well. Our planet presents a substantially larger gravitational target than the Moon, attracting more incoming objects and intercepting larger impactors. Although Earth's active geology erased nearly all direct traces from that distant era, the neighboring world preserves a minimum record of the bombardment shared by both bodies. The scars covering the Moon therefore establish the lowest estimate for what Earth endured, offering a durable reference against which the earliest chapters of our planet can still be understood. Among the countless collisions considered throughout this early chapter of Earth's history, A small number belong in a category entirely their own. These were not merely larger versions of familiar impacts. They represented encounters capable of transforming the entire planet within hours. Their effects extended far beyond a crater or a regional catastrophe, reaching every ocean, every coastline, and every part of the atmosphere. Scientists have examined what would happen if an asteroid measuring between approximately 50 and 100 kilometers across, which is about 31 to 62 miles, struck one of Earth's young oceans. The amount of energy released would exceed anything preserved within the recent geological record. Computer models indicate that such an impact could vaporize essentially the entire global ocean, an immense reservoir containing roughly 1.335 billion cubic kilometers of water. Instead of remaining as liquid, nearly all of that water would become intensely heated steam over the course of only a few hours. The atmosphere would then undergo a dramatic transformation. Rather than clouds drifting above a liquid ocean, Earth would become wrapped within a dense envelope of superheated water vapor. Temperatures could exceed 2,000 degrees Celsius, or 3,632 degrees Fahrenheit, preventing rain from reaching the surface for an immense span of time. Depending upon the exact size of the impactor and the conditions following the collision, this vapor-filled atmosphere might persist for hundreds or even thousands of years before cooling gradually enough for water to condense once more into lakes, rivers, and oceans. Conditions across the surface during that interval would have been extraordinarily hostile to biology. Any organisms living in exposed environments would encounter temperatures far beyond the limits tolerated by even the simplest known bacteria. Rocks near the surface would absorb enormous quantities of heat, while steam circulated continuously through the atmosphere before eventually radiating its energy into space. The planet would remain physically active throughout this prolonged cooling period, with liquid water unable to establish lasting stability until temperatures declined sufficiently. These possibilities were explored in influential research published during 1989 by Norman Sleep, Kevin Zonley, James Casting, and Harold Morowitz in the journal Nature. Their work introduced the phrase annihilation of ecosystems to describe the consequences of impacts large enough to vaporize Earth's oceans. Based upon available models, they concluded that several collisions of this magnitude may have occurred during the period of heaviest bombardment, although the precise number remains uncertain because so little direct evidence survives from Earth's earliest surface. Their study also offered an important qualification. Destruction at the surface would not necessarily extend throughout the entire planet. Beneath approximately 2 to 3 kilometers of solid rock, that is nearly 1.2 to 1.9 miles, temperatures could remain far lower than those above. Deep fractures, porous crust, and underground reservoirs might continue providing environments where heat from the impact failed to penetrate completely. Such locations, therefore, remained possible refuges despite the devastation unfolding overhead. Even these extraordinary collisions should not be viewed as inevitable features of the bombardment. Whether they occurred depended upon the number, composition, speed, and size of the largest incoming bodies. Researchers continue debating how frequently objects at this extreme end of the distribution actually struck Earth. The uncertainty surrounds their probability, not the underlying physics. If an impactor of sufficient scale reached the young planet, the conversion of global oceans into superheated steam follows naturally from well understood physical principles, marking one of the most profound transformations Earth could experience. Far below the battered surface, the planet followed a very different story. While impacts repeatedly transformed the world above, heat traveled through solid rock much more slowly than through the atmosphere or oceans. The crust acted as a powerful barrier, absorbing and dispersing energy before it could penetrate to greater depths. That simple physical property reshaped the scientific picture of Earth's earliest habitability and opened the possibility that life, if it had already emerged, possessed places where it could endure. Conditions at the surface during the bombardment remained unsuitable for long lasting communities of complex organisms. Large impacts repeatedly altered landscapes, disrupted climate, and, in the most extreme scenarios, could erase surface ecosystems across enormous regions. Yet, these destructive events did not affect every environment equally. As researchers began examining the thermal consequences of impacts beneath the ground, they discovered that survival depended as much upon depth as upon the impacts themselves. A major step toward understanding that hidden world came in 2009 through research conducted by Oleg Abramov and Stephen Mojesis at the University of Colorado. They developed an advanced three-dimensional computer simulation designed to reconstruct the bombardment across Earth's earliest history. Their model incorporated estimated impact frequencies, a realistic range of incoming object sizes, and calculations describing how each collision transferred heat into the crust and the upper mantle over time. The researchers first simulated the bombardment using the best available estimates for its actual intensity. They then created a far more demanding experiment by increasing the impact rate to 10 times the expected value. This extreme scenario intentionally exceeded most scientific reconstructions, allowing them to test whether even an exceptionally violent bombardment could completely sterilize the planet. The results proved remarkably resilient across both simulations. Even under the intensified conditions, approximately 73% of Earth's surface area never experienced temperatures above 110 degrees Celsius or 230 degrees Fahrenheit at appropriate depths beneath the surface. That temperature carries particular importance because it approaches the upper limit tolerated by many hyperthermophilic bacteria, meaning heat-loving microorganisms that flourish under extreme temperatures and have been discovered in environments including deep-sea hydrothermal vents and naturally heated geothermal springs. Although conditions above remained devastating, extensive underground regions retained temperatures compatible with the survival of these extraordinary forms of life. This conclusion fundamentally altered how many scientists interpreted the bombardment. Earlier discussions often treated the most severe impacts as events capable of sterilizing the entire planet. Abramov and Mojesis demonstrated that such an outcome was far less likely than previously imagined. Even when collisions became substantially more frequent within their simulations, large portions of the deep crust remained thermally protected. The distinction transformed the debate from one centered upon complete extinction to one focused upon the resilience of subsurface habitats. Several natural environments could have provided those refuges. Hydrothermal systems circulating hot mineral-rich water through fractured rock offered both warmth and chemical energy. Networks of deep crustal cracks created isolated pockets where groundwater persisted despite upheaval at the surface. Tiny spaces within solid rock itself supported communities of microorganisms in later geological eras, suggesting similar habitats may have existed much earlier. Kilometers of overlying stone, which is about miles of protective crust, shielded these environments from the worst effects unfolding overhead. Reducing the transfer of destructive heat and preserving conditions that remained surprisingly stable despite the relentless violence marking Earth's earliest age. If any setting consistently appears at the center of the search for Earth's earliest living systems, it is found far below the reach of sunlight. There, along fractures crossing the young ocean floor, water and rock met in an endless exchange driven by the planet's internal heat. These environments remain among the strongest candidates for the survival of early life during the bombardment, and perhaps even for life's first beginning. Hydrothermal vents are cracks in the ocean floor where seawater seeps downward through fractured crust, becomes heated by underlying magma, and rises back toward the seabed, carrying dissolved minerals gathered during its journey. Today, these systems occur along mid-ocean ridges and volcanic hotspots scattered across the world's oceans. They support rich biological communities, entirely independent of sunlight, relying instead upon chemical energy emerging from Earth's interior. The earliest Earth likely possessed far more of these systems than the modern planet. Its crust retained greater internal heat left from planetary formation, volcanic activity remained widespread, and the ocean floor was extensively fractured by continuous tectonic movement and repeated impacts. Every new crack allowed seawater to circulate deeper into the crust before returning through mineral-rich channels. Countless hydrothermal systems may therefore have operated simultaneously across the young seafloor, creating an extensive network of chemically active environments. Several characteristics made these locations unusually favorable for primitive biology. Water remained liquid because the immense pressure beneath the ocean prevented it from boiling despite extremely high temperatures. Chemical energy gradients, meaning differences in chemistry between hot vent fluids and the surrounding colder seawater, created continuous opportunities for simple chemical reactions to release usable energy. Dissolved minerals supplied essential ingredients that could participate in increasingly complex molecular processes. Together, these conditions formed natural laboratories where chemistry could persist over immense spans of time without depending upon sunlight reaching the surface. The surrounding geology also offered protection during periods of intense bombardment. Even if particularly large impacts disturbed the oceans above, great depths helped moderate their effects. Water under enormous pressure remained stable, while thick layers of crust absorbed and dispersed much of the mechanical energy transmitted through the planet. Local disruptions certainly occurred near major impacts, yet many deep hydrothermal systems may have continued operating despite repeated changes unfolding far overhead. Their persistence depended upon steady geothermal heat rather than the changing conditions at the surface. Evidence supporting the antiquity of such environments comes from the Barberton Greenstone Belt in South Africa. Rocks approximately 3.5 billion years old preserve sedimentary features and mineral assemblages associated with hydrothermal activity, providing one of the oldest surviving records of this style of environment. Although these rocks formed long after the earliest bombardment had begun to fade, they reveal that hydrothermal systems remained active across the young Earth, while occasional large impacts still influenced the planet. They preserve a geological glimpse into habitats that had already existed for an immense span of time. For many researchers, these deep environments represent far more than places of refuge. They offer continuous sources of heat, water, minerals, and chemical energy operating together within naturally enclosed spaces. Such conditions could support microorganisms through periods of planetary upheaval, while also encouraging increasingly sophisticated chemistry. Whether life first appeared within hydrothermal systems or merely found lasting shelter, there remains unresolved. Yet the ocean floor continues to provide one of the most convincing settings where Earth's earliest biological story could unfold, despite the restless world above. One of the most intriguing discoveries in Earth's earliest history emerges from placing two timelines beside one another. One traces a planet enduring repeated impacts across hundreds of millions of years. The other follows the earliest signs that living systems had already begun to leave subtle marks within rock. Where those timelines overlap, the familiar story of destruction gives way to something far more unexpected because life appears to have existed before, during, or immediately after the bombardment, and present evidence cannot yet determine which possibility is correct. The oldest widely accepted fossil record of life comes from the Dresser Formation in Western Australia. Within these rocks, dated to approximately 3.47 billion years ago, researchers have identified stromatolites, layered mounds constructed by communities of microorganisms, commonly photosynthetic cyanobacteria, that trapped and bound fine sediment as they grew. Their distinctive layered architecture reflects repeated biological activity over extended periods, preserving one of the clearest windows into Earth's earliest confirmed ecosystems. These fossils occupy an important place within the evolving chronology of the bombardment. By approximately 3.47 billion years ago, the greatest intensity of impacts had almost certainly faded. Even so, evidence suggests that large collisions had not disappeared entirely. Earth therefore supported established microbial communities, while occasional major impacts still occurred elsewhere across the planet. Life did not emerge only after every danger had passed. It occupied a world that continued to experience geological disturbance inherited from its earliest history. Other discoveries suggest the biological story may extend even farther into the past. A zircon crystal dated to approximately 4.1 billion years ago contains carbon inclusions whose chemical characteristics have attracted considerable attention. Some researchers propose that this carbon may have been processed by living organisms before becoming enclosed within the growing crystal. Should that interpretation eventually withstand continued examination, biological activity would have existed at least 400 million years before the oldest confirmed fossil structures currently known. Additional evidence comes from the chemistry preserved within some of Earth's oldest surviving rocks. Several studies, examining rocks approximately 3.85 billion years old, have identified carbon displaying isotopic characteristics commonly associated with biological processing. Living organisms generally favor lighter forms of carbon during metabolism, leaving behind a recognizable chemical pattern. Similar signatures appearing in these ancient rocks have therefore been interpreted by many investigators as indirect evidence that biological activity had already become established remarkably early in Earth's history. That interpretation remains actively debated. Some scientists argue that hydrothermal reactions occurring without biology can also produce comparatively light carbon under particular conditions. According to this view, the isotopic evidence alone cannot establish the presence of living organisms with complete confidence. Other researchers conclude that biological activity remains the most straightforward explanation because it accounts naturally for the observed chemical patterns while remaining consistent with additional geological observations. The discussion continues because both interpretations draw upon plausible physical processes, and the surviving evidence from this distant era remains exceptionally limited. Taken together, these discoveries present a remarkable paradox. If life truly flourished, while substantial impacts still reshaped parts of Earth's surface, then early organisms possessed resilience beyond earlier expectations. Another possibility places life's origin within protected environments where the consequences of bombardment rarely penetrated. Both ideas may even prove compatible, describing organisms that first appeared within sheltered habitats before spreading gradually across a changing planet. The oldest traces of biology, therefore, stand beside the record of cosmic collisions, revealing that Earth's earliest living chapter unfolded alongside one of the most dynamic periods in planetary history. Every object that descended from the young solar system carried more than destructive force. Locked within many of those wandering bodies were ingredients gathered far from the growing Earth, preserved through immense stretches of time and distance. As collisions reshaped the planet's surface, they also transferred materials that Earth itself may never have possessed in abundance during its earliest formation, creating an unexpected partnership between devastation and renewal. Planetary scientists have long recognized that the earliest Earth formed relatively close to the Sun, where temperatures remained high enough to discourage the accumulation of many volatile compounds. Water, along with other easily vaporized substances, would have been scarce within much of the rocky material assembling the young planet. According to a leading hypothesis, large numbers of ice rich comets scattered inward from the outer solar system during the planetary rearrangement described by the NICE model. As these icy visitors struck Earth across the era of heavy bombardment, they delivered substantial quantities of frozen water that ultimately contributed to the oceans covering the modern world. The exact fraction supplied through this process remains actively investigated, and alternative explanations continue to receive careful study. Some water almost certainly originated from hydrated minerals incorporated during planetary growth. Even so, many researchers conclude that repeated impacts from distant objects supplied an important share of Earth's present inventory. The bombardment, therefore, helped transform a comparatively dry, rocky planet into one where liquid water became a defining feature of the surface. Those incoming bodies carried far more than frozen water. Carbonaceous asteroids, among the most chemically rich objects in the solar system, preserve an extraordinary collection of organic compounds. Analyses have identified amino acids, hydrogen cyanide, formaldehyde, methanol, and molecular precursors that participate in forming nucleic acids, the compounds that create the structural backbone of deoxyribonucleic acid and ribonucleic acid. These substances represent fundamental building materials for biological chemistry, arriving naturally without requiring living organisms to produce them beforehand. Direct evidence for this remarkable chemical cargo arrived through a modern sample return mission. During 2020, the Japanese Hayabusa 2 spacecraft returned carefully sealed material collected from the asteroid Ryugu. Laboratory examination revealed intact amino acids together with nicotinic acid, also known as vitamin B3. These discoveries demonstrated that delicate organic molecules can survive prolonged exposure to space and remain preserved inside primitive asteroids until reaching a suitable planetary surface under favorable conditions. Laboratory experiments have also revealed another intriguing possibility. Researchers at Lawrence Livermore National Laboratory investigated what happens when comets strike a planet at relatively shallow angles. Their results indicated that the enormous pressures generated during impact compression can create glycine, the simplest amino acid within portions of the comet itself. Under appropriate impact conditions, the collision becomes more than a transport mechanism. The physical forces released during the event actively generate additional organic molecules before dispersing them across the target world. Viewed through this broader perspective, the bombardment assumes a more complex role within Earth's history. Every impact represented an exchange between worlds, carrying water, carbon rich compounds, and molecular ingredients assembled across distant regions of the solar system. Some collisions undoubtedly erased existing environments, while others expanded the chemical possibilities available to the recovering planet. The same era remembered for relentless impacts also became the greatest episode of molecular delivery Earth has ever experienced, enriching the young world with materials that later biological processes could transform into something entirely new. A collision does not end when the crater forms. The first moments unfold with overwhelming force, yet the geological consequences continue long after the brilliant flash has faded. Beneath shattered ground and newly melted rock, heat lingers, water begins to circulate, and a fresh environment gradually develops. Within these evolving landscapes, some researchers see conditions that may have encouraged the earliest steps toward biology itself. When a large impactor strikes an ocean, the immense energy released fractures the surrounding crust and leaves behind enormous reservoirs of heat. Seawater gradually seeps into these broken rocks, becomes heated deep below the crater, dissolves minerals from the surrounding material, and eventually rises again through newly opened pathways. Scientists describe this process as an impact-induced hydrothermal system, meaning the circulation of superheated water through fractured and melted rock surrounding a large impact crater. Depending upon the size of the impact and the amount of remaining heat, such systems may continue operating for tens of thousands or even hundreds of thousands of years. These environments resemble hydrothermal vents found along the modern ocean floor in several important ways. Both circulate mineral rich fluids through porous rock while maintaining elevated temperatures and active chemical exchange. There is, however, one important difference. Mid-ocean ridge systems develop only where geological conditions naturally support them. Impact-generated hydrothermal systems can appear almost anywhere. A sufficiently large collision occurs, creating chemically active environments across a much broader range of landscapes and seafloor settings. Every new crater, therefore, represented more than a scar upon the planet. It also established a temporary laboratory where heated water interacted continuously with freshly fractured minerals. Chemical compounds dissolved, combined, separated, and recombined under changing conditions that differed from one crater to another. Variations in rock composition, water chemistry, and temperature produced distinct local environments, allowing many different reaction pathways to unfold simultaneously instead of concentrating every possibility within a single location. This broader perspective has attracted increasing scientific attention. Research published in the journal Marine Geology proposes that impact-generated hydrothermal systems may have ranked among the most widespread settings for prebiotic chemistry during the era of heavy bombardment. Prebiotic chemistry refers to the natural chemical processes that precede and enable the emergence of living systems. Within these warm circulating fluids, simple molecules could encounter favorable conditions for assembling into increasingly complex compounds over extended periods, supported by continuous supplies of heat, dissolved minerals, and chemical energy. The duration of these systems proved especially important. Unlike the brief violence of the initial collision, hydrothermal circulation persisted across immense spans of time. A crater that formed within moments could sustain chemically active groundwater for many thousands of years afterward, sometimes much longer. During that interval, countless microscopic reactions occurred repeatedly within interconnected networks of pores, fractures, and mineral surfaces each interaction providing another opportunity for greater chemical complexity to emerge. Viewed together across the young Earth, these craters formed an extraordinary planetary mosaic. Every sufficiently large impact established another temporary chemical reactor operating independently while differing slightly in temperature, mineral content, and circulating fluids. Some undoubtedly remained unsuitable for biological precursors, while others may have offered unusually favorable combinations of conditions. Collectively, they expanded the range of chemical experiments unfolding across the planet, increasing the opportunities for self replicating molecular systems to arise within environments shaped, quite unexpectedly, by the same impacts that had transformed Earth's earliest surface. Perspective often arrives through comparison. The scars preserved on neighboring worlds reveal that Earth's early history was never an isolated event, but part of a transformation shared across the inner solar system. Each rocky planet encountered the same wandering populations of asteroids and comets. Each absorbed countless collisions. Yet the landscapes left behind tell remarkably different stories about what followed after the impacts ended. Mercury offers perhaps the clearest surviving archive of that violent era. Orbiting closest to the Sun, it possesses almost no atmosphere, no flowing water, and no system of moving crustal plates capable of renewing its surface. Once an impact crater forms, little exists to erase it. Generation after generation of collisions accumulated upon one another until the planet became a nearly complete geological record of the earliest solar system. Looking across Mercury is like examining a museum whose exhibits have remained largely undisturbed for billions of years. Among its greatest landmarks stands the Caloris Basin, measuring approximately 1,550 kilometers across, which is about 963 miles. Formed during the period associated with the heavy bombardment, this immense structure ranks among the largest confirmed impact basins in the solar system. The collision released so much energy that seismic waves traveled completely around the planet before converging at the point directly opposite the impact. There, the crust fractured into an extraordinary landscape of broken ridges and disrupted hills known as chaotic terrain, sometimes informally described as the weird terrain because of its unusual appearance. Mars preserves another chapter of the same history. Its southern hemisphere contains some of the oldest exposed terrain in the solar system, densely covered with craters accumulated across immense spans of time. The northern hemisphere presents a striking contrast, appearing lower in elevation and comparatively smoother across broad regions. Planetary scientists describe this difference as a geological dichotomy, meaning a sharp division in the nature of the two hemispheres of the same planet. One leading explanation proposes that one or more truly enormous impacts helped shape this remarkable global contrast during the planet's earliest evolution. Venus provides a more challenging puzzle. A dense atmosphere conceals much of its surface from ordinary observation, while widespread volcanic resurfacing has buried much of its earliest geological record beneath younger lava plains. Direct evidence for the bombardment, therefore, remains difficult to preserve or identify. Even so, crater counts, geological mapping, and reconstructions of volcanic history indicate that Venus also experienced the same broad period of intense impacts affecting the neighboring rocky planets. Taken together, Mercury, Venus, Mars, and Earth shared a common bombardment, yet their later histories diverged dramatically. Mercury preserved nearly every wound. Mars retained many, while evolving into a colder, drier world. Venus repeatedly renewed its surface through volcanism until much of its earliest record disappeared. Earth followed another path altogether, continually reshaping its crust through plate tectonics while sustaining long lasting oceans and an active climate capable of recycling ancient landscapes. As far as present evidence reveals, none of Earth's neighbors developed living systems that transformed their worlds in the way biology transformed ours. Earth alone became a planet where geology and life evolved together across billions of years. The bombardment itself cannot explain that outcome because every neighboring world endured the same celestial assault. The deeper mystery lies in understanding which combination of water, internal activity, chemistry, and environmental stability allowed one planet to preserve conditions where living systems could continue while the others remained worlds of stone. The final stones did not fall when the bombardment ended. Their passage left lasting patterns across the solar system, preserving evidence within planetary orbits, scattered debris, and populations of surviving worlds. The familiar arrangement seen today is therefore not the original design. It is the enduring outcome of a period when gravity reshaped nearly every major region surrounding the Sunday. The outer planets once occupied a noticeably different configuration from the one observed today. According to the prevailing model, Uranus and Neptune formed closer to the Sun before the gravitational instability unfolded. As the giant planets exchanged momentum with countless smaller bodies, their paths shifted outward through a prolonged sequence of encounters. Computer simulations indicate that Uranus and Neptune may even have exchanged orbital positions during this migration, an extraordinary rearrangement that left each planet traveling far from its birthplace before eventually settling into long term stability. Jupiter also experienced important changes during this era. As its orbit evolved, the giant planet trapped large collections of rocky bodies into special regions where gravity created lasting balance. These groups became known as the Trojan asteroids, populations of rocky objects locked within stable Lagrangian points, positioned approximately 60 degrees ahead of and 60 degrees behind a planet along its orbit around the Sunday. Protected within these gravitational sanctuaries, many of these asteroids have remained remarkably unchanged since the earliest stages of planetary evolution. Because they escaped the widespread clearing that affected many other regions, Jupiter's Trojan asteroids preserve valuable information about conditions during the bombardment era. Their compositions, structures, and orbital characteristics serve as surviving records from that distant time. The National Aeronautics and Space Administration launched the Lucy mission during 2021 to explore several of these ancient bodies directly, seeking clues about the material present when the giant planets migrated and the bombardment reshaped the inner solar system. Far beyond Neptune, another transformation unfolded across the primordial Kuiper Belt. Before planetary migration disrupted this region, researchers estimate that it contained material equivalent to approximately 30 Earth masses. Gravitational encounters scattered enormous quantities of that debris outward into interstellar space, inward toward the giant planets, or onto entirely different orbital paths. Only a small fraction of the original population remained behind. The sparse Kuiper Belt observed today, therefore, represents the surviving remnant of a once far richer reservoir of icy bodies. Closer to the Sun, the asteroid belt also acquired its modern appearance through this same sequence of events. An important population occupying the inner portion of the belt, commonly called the E-belt, became destabilized as planetary orbits shifted. Many of these objects collided with planets or escaped into new trajectories, leaving that region largely emptied. The remaining asteroid belt became thinner overall, while developing the compositional zones that astronomers continue to study today, reflecting differences in where various groups of objects originally formed. When these changes finally subsided, the solar system entered a far more orderly state. Vast numbers of small bodies had disappeared through collisions, ejection, or permanent relocation. Planetary orbits settled into configurations that have remained comparatively stable for approximately 3.8 billion years. The familiar architecture surrounding the Sun, from the distant Kuiper Belt to the Trojan asteroids accompanying Jupiter, still carries the imprint of that profound gravitational reshaping. The bombardment altered far more than Earth's history. It established the long-lasting structure of the planetary family that continues to endure today. History often prefers clear endings. A chapter closes, one era yields to the next, and the landscape appears transformed in a single, decisive moment. The geological record tells a different story. The period known as the Late Heavy Bombardment did not conclude with a final impact followed by lasting calm. Its decline unfolded gradually, stretching across immense spans of time as the remaining debris of the young solar system continued to cross Earth's path with decreasing frequency. Traditional descriptions often portray the bombardment as reaching a dramatic peak before settling into the comparatively stable conditions that characterize the modern inner solar system. That broad outline remains useful, yet the surviving evidence suggests a slower transition. Instead of an abrupt boundary separating one age from another, the record points toward a prolonged fading. Large impacts became less common over hundreds of millions of years, though they never disappeared immediately after the principal episode had passed. Some of the strongest evidence comes from Earth itself. Ancient rock formations preserve unusual layers composed of tiny spherical particles produced when enormous impacts melted and vaporized rock before ejecting droplets high into the atmosphere. As these droplets cooled, they solidified into minute spheres and later settled back onto the surface, becoming trapped within accumulating sediments. These deposits are known as impact spheral layers, providing durable geological markers of collisions that occurred billions of years ago. Many of these remarkable layers survive within rocks dating from the Precambrian, the geological eon, extending from Earth's formation until approximately 541 million years ago and encompassing the overwhelming majority of our planet's history. Although Earth's active geology has erased countless traces of early impacts, a limited number of these ancient deposits escaped destruction, preserving evidence that otherwise would have vanished through plate tectonics, erosion, and metamorphism. Research published in the journal Nature during 2012 examined impact spheral layers preserved within rocks, approximately 3.47 billion years old and 3.22 billion years old. By analyzing the distribution and characteristics of these tiny particles, investigators estimated the sizes of the impactors responsible for producing them. Their quantitative modeling indicated collisions powerful enough to vaporize portions of Earth's oceans temporarily, despite occurring well after the principal phase of the late heavy bombardment had largely subsided. These discoveries suggest that the bombardment possessed a remarkably extended conclusion. The largest collisions became increasingly uncommon, yet isolated impacts of extraordinary scale still punctuated Earth's history long afterward. Each represented the lingering passage of surviving objects that continued orbiting the Sun, remnants of a once much denser population gradually being eliminated through collisions, planetary encounters, or permanent ejection from the solar system. This prolonged decline shaped the environment experienced by the earliest flourishing biosphere. During the Archean eon, The geological interval, extending from approximately 4 billion years ago until 2.5 billion years ago, life expanded across a planet that had entered a more stable phase without ever becoming completely free from celestial disruption. Organisms adapted, diversified, and persisted, while occasional giant impacts still interrupted the ordinary rhythms of the surface. The ending of the bombardment therefore resembled a gradual settling rather than a decisive conclusion. Across hundreds of millions of years, the intervals between major impacts steadily lengthened until they became measured in extraordinary spans of geological time. By then, Earth had already begun another chapter of its history, carrying forward both the scars and the opportunities left behind by a fading storm whose final echoes lingered long after its greatest violence had passed. The earliest unmistakable chapter of Earth's biological story appears with surprising confidence. After billions of years recorded only through scattered chemical traces and fragmentary clues, the rocks finally preserve structures that speak with far greater clarity. They reveal living communities already established, already interacting with their surroundings, and already shaping the landscapes in which they existed. These remarkable fossils come from the Dresser Formation within the Pilbara region of Western Australia, where rocks, approximately 3.47 billion years old, preserve the oldest undisputed fossil evidence of life currently known. They take the form of stromatolites, layered microbial mounds constructed as communities of bacteria grew across shallow environments, trapping fine sediment and binding loose particles into gradually rising structures. Layer upon layer, accumulated through countless cycles of biological activity, leaving behind a durable record that survived almost unimaginably long stretches of geological time. Although they represent the oldest confirmed fossils, these formations do not portray biology taking its first uncertain steps. Their internal organization reflects communities capable of coordinating growth across broad microbial mats while responding continuously to changing environmental conditions. Individual microorganisms interacted with surrounding water, minerals, sunlight, and one another, gradually building three-dimensional architectures whose layered patterns reveal sustained cooperation extending across many generations. Such organization reflects biological systems that had already undergone considerable evolutionary development before becoming preserved within stone. This realization shifts the timeline of life's history farther into the past. If organisms capable of constructing stromatolites flourished by approximately 3.47 billion years ago, then the origin of life must have preceded these fossils by an interval that remains uncertain. Whether that interval measured tens of millions or several hundreds of millions of years continues to be debated. Regardless of its exact duration, the fossil record begins only after evolution had already transformed the earliest living systems into resilient and organized communities. Their existence also overlaps with the lingering decline of planetary bombardment. Earth had entered a more stable age than before, yet occasional large impacts still interrupted the ordinary processes unfolding across the surface. Microbial ecosystems therefore expanded upon a world where rare collisions continued to reshape portions of the environment. The earliest confirmed biosphere did not inhabit a completely settled planet. Instead, it developed while the final remnants of an earlier celestial upheaval gradually diminished across geological time. As biological diversity increased, these microscopic organisms began influencing the planet in ways no geological process could accomplish alone. Among the most significant were photosynthetic bacteria that captured energy from sunlight while releasing oxygen as a byproduct of their metabolism. By approximately 2.7 billion years ago, their collective activity had become substantial enough to alter the chemistry of Earth's atmosphere. Oxygen accumulated gradually across oceans and air, initiating one of the greatest environmental transformations in planetary history. For many organisms already living without oxygen, this change introduced profound challenges because the newly abundant gas proved chemically harmful to biological systems adapted to entirely different conditions. At the same time, the growing oxygen supply opened opportunities for future forms of metabolism capable of extracting far greater amounts of energy from food. Across immense spans of time, this atmospheric transformation prepared the foundation for increasingly complex life while reshaping the chemistry of oceans, rocks, and sky alike. Earth's earliest enduring biosphere therefore achieved far more than persistence. From modest microbial communities emerged biological processes powerful enough to redirect the evolution of an entire planet. The world inherited from the fading bombardment became the stage upon which life steadily transformed geology into biology, and biology into a new planetary chemistry whose influence continues to surround us today. Some of the most important influences upon Earth's history arrived before the first chapter of the bombardment had even begun. Long before asteroids and comets reshaped the young planet, another event established a partnership that would endure across billions of years. Earth's nearest companion became more than a familiar presence in the sky. It helped shape the conditions under which the planet itself continued to evolve. Current evidence indicates that the Moon formed approximately 4.5 billion years ago when a body about the size of Mars, known as Theia, collided with the young proto-Earth. The impact released extraordinary amounts of energy, vaporizing immense volumes of rock and sending molten debris into orbit around the damaged planet. Over time, this expanding cloud gradually gathered together through gravity until it formed a single, large, natural satellite. The collision permanently altered both worlds, creating a relationship unlike any other among the rocky planets. The newborn moon did not orbit at its present distance. During its earliest history, it traveled perhaps 10 to 20 times closer to Earth than it does today. At such proximity, gravitational attraction generated exceptionally powerful tides. Oceans rose and fell across much greater ranges, while the solid crust itself flexed under repeated tidal stresses. This continual deformation released heat within Earth's interior, adding another source of energy alongside radioactive decay and the lingering warmth retained from planetary formation. That sustained geological activity may have carried consequences extending well beyond volcanic eruptions and crustal recycling. A warm, active interior helps maintain vigorous circulation within Earth's liquid metallic outer core. The movement of electrically conductive material inside that deep region generates the planetary magnetic field through a natural dynamo process. Surrounding Earth, this magnetic field extends outward into space, creating the magnetosphere, the region around a planet dominated by its magnetic field, where charged particles from the Sun are redirected before reaching the atmosphere below. The magnetosphere serves as an important protective boundary against the continuous stream of electrically charged particles known as the solar wind. Without such magnetic protection, those particles can gradually erode a planet's upper atmosphere across immense spans of time. Mars provides evidence that atmospheric loss can become substantial after a global magnetic field weakens. During Earth's youth, when solar activity exceeded modern levels, preserving a strong magnetic shield may have been especially significant for maintaining the atmosphere through an era already challenged by repeated impacts. Large collisions also interacted with the atmosphere in complex ways, ejecting gases into space while simultaneously delivering new volatile materials from incoming bodies. A durable magnetosphere could not prevent every atmospheric loss caused by impacts, yet it reduced the additional erosion driven by the persistent solar wind. In that sense, the Moon's influence upon Earth's internal dynamics may have indirectly strengthened the long term stability of the air surrounding the planet, preserving conditions that later biological evolution would depend upon. The Moon itself followed a different path, lacking active plate tectonics and extensive geological renewal. It retained the scars of the bombardment across its surface, while Earth gradually erased many of its own. Those preserved craters eventually revealed the existence of the bombardment that had shaped both worlds. The companion born from an earlier planetary collision became both witness and archive, carrying an enduring record of the events that transformed the young solar system while contributing, through its remarkable partnership with Earth, to the conditions that allowed life to persist and flourish. With the passage of approximately 4 billion years, the scattered pieces of Earth's early story begin to assemble into a broader picture. No single event explains why one world became filled with living systems while nearby planets followed very different paths. Instead, several enduring qualities worked together, each strengthening the others until the recovering planet possessed an unusual capacity for long term stability. Earth's size formed one of those essential foundations. It was massive enough to retain substantial internal heat over immense spans of time, sustaining vigorous motion within its metallic core. That circulation generated a durable magnetic field capable of surrounding the planet with lasting protection. Earth's gravity also proved strong enough to hold onto a substantial atmosphere, despite repeated erosion caused by large impacts and the continual influence of the solar wind. A smaller world would have struggled to preserve these advantages through billions of years of planetary evolution. Its interior also supported another remarkable process that appears unique within the solar system on Earth's extraordinary scale and longevity. Plate tectonics, the slow movement of large sections of Earth's crust, called plates, driven by convection within the underlying mantle, continually reshaped the planet's surface. Ocean basins opened while others disappeared. Mountain ranges rose and gradually wore away. Ancient crust descended into the mantle as newly formed crust emerged elsewhere, creating an uninterrupted cycle that renewed Earth's outer shell across geological ages. This constant recycling extended beyond rock alone. Carbon moved repeatedly between the atmosphere, oceans, crust, and mantle through volcanic activity, weathering, and plate motion. Such exchanges helped regulate Earth's long term climate despite the gradual brightening of the sun over billions of years. Without this balancing system, atmospheric conditions could have drifted toward extremes that either froze surface water for prolonged intervals or heated the planet beyond the stability required for widespread liquid water. Earth also occupied an exceptionally favorable location around the Sunday. It traveled within the habitable zone, the range of orbital distances from a star where liquid water can exist stably upon a planetary surface, sometimes called the Goldilocks zone. Following major impacts and the gradual restoration of surface conditions, temperatures could return to values that once again supported extensive oceans instead of maintaining permanent ice or persistent global evaporation. This fortunate position allowed water to remain available through changing stages of planetary history. Another contribution came from the companion that had accompanied Earth since its earliest youth. The moon exerted a continuing gravitational influence upon Earth's axial tilt, the angle between the planet's rotational axis and the plane of its orbit around the Sun, which determines the severity of seasonal changes. Computer models indicate that without a large stabilizing satellite, Earth's axial tilt might have varied dramatically across time. Such extreme shifts could have produced severe climatic fluctuations, repeatedly disrupting environments already recovering from earlier planetary upheavals. Together, these characteristics reinforced one another across immense intervals. A favorable orbit preserved surface water. Plate tectonics renewed the crust while moderating atmospheric carbon. A sustained magnetic field protected the atmosphere from gradual erosion. The moon steadied Earth's rotational orientation, helping maintain relatively consistent climatic patterns. None alone guaranteed the emergence of life, yet each reduced obstacles that might otherwise have prevented long-lasting biological evolution. Looking across the neighboring planets reveals worlds that possess some of these qualities, but not all of them together. Earth's distinction, therefore, emerged through an uncommon combination of enduring advantages. As the bombardment gradually faded into geological memory, those intertwined systems continued operating without interruption, allowing a once battered planet to develop into a world where oceans, atmosphere, geology, and living organisms remained linked through a shared history that continues even now. Sometimes the greatest discoveries arrive in the smallest forms. A single crystal, scarcely larger than a grain of sand, can preserve memories that entire mountain ranges have long since lost. Within such tiny fragments, Earth's earliest history survives with astonishing fidelity, carrying chemical records from an age whose landscapes disappeared billions of years ago. The zircon crystals recovered from the Jack Hills of Western Australia have become far more than unusual geological specimens. Their extraordinary durability allows them to endure repeated cycles of burial, uplift, erosion, and renewal while retaining chemical information from the moment they first crystallized. Because so little rock from Earth's earliest history remains intact, these resilient minerals have become rare witnesses to conditions that no longer exist anywhere upon the planet's surface. One remarkable zircon formed approximately 4.4 billion years ago, while Earth itself was still assembling into a mature world and before the principal bombardment had begun. Careful analysis of its oxygen isotopes suggested that the crystal crystallized in the presence of liquid water and a crust that had already cooled enough to interact with that water. Such evidence challenged the long accepted picture of an entirely molten young Earth, indicating instead that stable environments may have emerged surprisingly early after planetary formation. Another zircon, dating from approximately 4.1 billion years ago, belongs to a different chapter. By then, the bombardment had already become an important force shaping the young planet. Within this crystal, scientists identified a carbon signature that some researchers interpret as potentially consistent with biological activity. That interpretation remains debated, and alternative explanations continue to be explored with equal care. Even so, the possibility itself carries profound significance because it suggests that chemistry associated with living systems may have existed while enormous impacts still occurred across the solar system. These crystals encourage a more careful view of the boundaries, often drawn within Earth's earliest history. Terms such as habitable and uninhabitable, or before life and after life, imply clear transitions that the surviving evidence does not always support. The geological record preserved within zircons instead points toward overlapping conditions, where environments favorable for complex chemistry may have appeared, disappeared, and returned repeatedly as the planet continued evolving. This perspective also reshapes understanding of the Hadean eon, the geological eon extending from Earth's formation approximately 4.54 billion years ago until 4 billion years ago, named after Hades from Greek tradition because scientists once imagined it as a uniformly hostile underworld. Modern evidence suggests a more intricate reality. Between episodes of intense planetary disturbance, intervals may have existed during which stable crust, liquid water, and chemically favorable environments endured long enough for increasingly complex reactions to unfold beneath the surface or within protected aquatic settings. The Hadean therefore appears less like an uninterrupted furnace and more like a world defined by powerful contrasts. Surface regions could experience catastrophic destruction, while distant environments remained comparatively suitable for sustained chemical evolution. Some locations undoubtedly became uninhabitable for extended periods, whereas others may have continued supporting persistent molecular experimentation despite upheaval elsewhere. Conditions varied across both place and time, instead of remaining fixed within a single planetary state. Within these enduring zircon crystals, the earliest Earth reveals itself with greater subtlety than earlier generations imagined. Their chemical signatures suggest a planet capable of alternating between disruption and opportunity, where destruction never entirely erased possibility. Across billions of years, these tiny minerals have preserved evidence that Earth's beginning was shaped less by simple extremes than by an intricate balance between instability and resilience, a balance that ultimately allowed the long story of life to continue unfolding. Scientific understanding rarely advances by replacing every uncertainty with certainty. More often, each discovery sharpens the questions that remain. After decades of studying ancient rocks, lunar samples, orbital measurements, and numerical simulations, the story of the Late Heavy Bombardment has become clearer in many respects. At the same time, several of its most important chapters continue to resist a final explanation. One enduring uncertainty concerns the overall character of the bombardment itself. Some researchers continue to support the idea of a relatively concentrated episode during which impact rates increased dramatically before declining. Others argue that the evidence is better explained by a long, uneven decrease in collisions, beginning much earlier and continuing across hundreds of millions of years. These competing interpretations influence far more than the history of impacts alone. They shape our understanding of the environments in which the earliest chemistry and biology developed. The timing of the greatest bombardment also remains unsettled. Traditional interpretations place the principal peak near approximately 3.9 billion years ago, largely from studies of lunar samples collected during the Apollo missions. Alternative models suggest that the most intense interval may have occurred closer to 4.48 billion years ago, with later impacts representing the gradually diminishing remnants of an earlier period of instability. Between these possibilities lies a wide span of planetary history whose precise sequence has yet to be fully reconstructed. The earliest history of life remains equally uncertain. Chemical signatures preserved within one zircon, dating from approximately 4.1 billion years ago, have been interpreted by some investigators as potentially consistent with biological activity. Others conclude that non-biological processes could have produced similar chemical patterns. Current evidence cannot resolve that disagreement with confidence. Whether living systems already existed during portions of the bombardment, or whether life emerged only after conditions became more stable, remains one of the most significant unanswered questions in Earth science. The origin of Earth's water also continues to invite careful investigation. Some portion almost certainly arrived within water rich asteroids and comets striking the growing planet. Additional water may have escaped from Earth's interior through volcanic outgassing as the young world cooled. Another contribution may have been retained from the original materials that assembled the planet itself. Determining the relative importance of these different sources remains challenging because each process unfolded across immense spans of geological time and left overlapping chemical evidence. Resolving these uncertainties depends upon gathering new evidence instead of relying solely upon existing collections. The Moon remains the most complete surviving archive of the bombardment, yet the samples studied in greatest detail originated from only a limited number of landing sites. Vast regions have never been explored directly. Among the most valuable targets are the lunar far side and the immense South Pole Aitken Basin, one of the oldest and largest impact structures in the solar system. Rocks preserved there may contain records unavailable anywhere else. The National Aeronautics and Space Administration Artemis program seeks to return human explorers to the Moon for the first time since 1972. Alongside its broader objectives, the program includes scientific investigations designed to collect samples from previously unexplored regions, capable of refining the chronology of lunar impacts. Those future specimens may reveal details hidden for billions of years, allowing Earth's earliest history to be understood with greater confidence while reminding us that even the oldest stories can continue growing as new evidence is patiently brought home. The history traced across Earth's earliest ages gradually widens beyond a single planet. Each discovery preserved within lunar rock, ancient minerals, or deeply weathered crust points toward a larger realization. The bombardment belonged to an event that reached across the inner solar system, touching every rocky world orbiting the young Sunday Earth's experience, was one chapter within a much broader planetary story. The migrations of the giant planets reshaped countless smaller bodies throughout the developing solar system, redirecting asteroids and comets onto new paths. Earth received its share of those encounters, yet Mercury, Venus, Mars, and the Moon also endured the same period of repeated collisions. Observations of planets forming around distant stars now suggest that orbital rearrangements among giant planets may occur frequently during planetary evolution. If such instabilities are common, then bombardments resembling this one may represent a familiar stage in the history of rocky worlds, rather than an unusual exception. Mars offers one of the most compelling comparisons. During the Noachian period, the earliest geological era of Mars, extending from approximately 4.1 billion years ago until 3.7 billion years ago, the planet possessed abundant evidence of flowing water, a denser atmosphere than exists today, and landscapes shaped by rivers, lakes, and groundwater. Craters formed alongside valley networks, mineral deposits, and sedimentary rocks, indicating that liquid water remained present across substantial portions of the Martian surface, despite the continuing record of impacts. If Earth provided an opportunity for biology to emerge during or soon after the bombardment, then early Mars may have experienced a comparable interval. The same incoming asteroids and comets that carried water, carbon-containing compounds, and other ingredients to Earth also struck Mars. Similar chemical materials, therefore, reached both planets, while each still possessed environments capable of supporting liquid water. Whether those ingredients followed the same path afterward remains unknown, yet the possibility broadens the search for life's beginnings beyond a single world. An even more intriguing idea considers whether biology itself might have traveled between neighboring planets. Powerful impacts occasionally accelerate fragments of planetary crust to speeds sufficient for escape into space. Some of those rocks eventually intersect the orbit of another planet, surviving the journey before falling once again to a surface. Scientists describe this process as lithopanspermia, the transfer of life between planets through meteorites. Laboratory studies and computer simulations indicate that certain microorganisms could potentially survive portions of such remarkable voyages if protected within solid rock. Evidence already confirms that pieces of Mars have reached Earth naturally. Numerous meteorites discovered upon our planet originated on the Martian surface before ancient impacts launched them into interplanetary space. Calculations indicate that material has almost certainly traveled in both directions over billions of years. If microscopic life existed on either world during the bombardment, exchanges of rock between Earth and Mars may also have carried living organisms or dormant cells across the space separating the two planets. Viewed from this wider perspective, the bombardment becomes more than the opening chapter of Earth's own biological history. It represents a process that may unfold wherever rocky planets form beside migrating giant worlds. Planetary systems throughout the galaxy could pass through similar intervals of collision, recovery, chemical enrichment, and environmental renewal. In that sense, Earth's earliest story may also serve as a guide for recognizing how life begins, persists, and perhaps even journeys between neighboring worlds after the first turbulent ages of planetary formation gradually give way to enduring stability. There comes a point when measurements, mineral analyses, crater counts, and orbital models begin to point toward something larger than themselves. The evidence remains firmly scientific, yet together it invites reflection upon continuity. Across time, the Late Heavy Bombardment is more than an event recorded in stone. It is part of the deeper story, explaining why any living creature exists upon Earth today. Later chapters of Earth's history contain catastrophes of astonishing scale. The end Permian extinction eliminated approximately 96% of marine species, transforming nearly every ecosystem in the oceans. Much later, the Cretaceous Paleogene extinction ended the age of the non-avian dinosaurs and reshaped life upon land and sea alike. These events stand among the greatest biological crises ever documented, yet they all occurred within approximately the last 540 million years, the interval during which complex animals flourished across the planet. The bombardment belongs to a far older chapter, separated from those extinctions by billions of years. Its duration extended across immense spans of time, and its cumulative effects reached every part of the young Earth. Entire landscapes disappeared and reformed. Atmospheres changed repeatedly. Oceans experienced profound disruption. Measured by the scale of planetary transformation, it exceeded any later biological crisis because it unfolded while the world itself was still becoming capable of sustaining enduring life. Despite that extraordinary upheaval, continuity emerged instead of permanent interruption. Somewhere within the diversity of environments that existed across the recovering planet, chemistry capable of reproducing itself continued from one generation to the next. Whether sheltered within deep fractures of the crust, sustained around hydrothermal systems, or preserved inside temporary habitats that reappeared between major impacts, the chain endured. Each successful cycle created the possibility for another, preserving a lineage whose earliest links remain hidden from direct observation. Every organism now living belongs to that same uninterrupted inheritance. Bacteria dividing within deep sediments, forests exchanging gases with the atmosphere, whales crossing the oceans, insects moving through flowering plants, and human cells, renewing themselves, all participate in a biological continuity, extending backward through every previous generation. That succession reaches beyond familiar history into an interval when the earliest ancestors of all later life persisted through conditions unlike anything experienced since. No individual organism survived across billions of years. Instead, survival belonged to information carried within living systems, copied repeatedly from one generation into the next. Each successful reproduction extended a chain already unimaginably long. Countless branches later disappeared, while others continued, diversified, and eventually produced every species known today. Across that immense passage of time, the continuity itself proved more durable than any single organism could ever become. The bombardment therefore illuminates resilience expressed through inheritance rather than permanence. Rocks fractured, continents changed, atmospheres evolved, and oceans transformed. Yet biological continuity adapted alongside those changes whenever conditions allowed. The history preserved in ancient minerals and lunar landscapes ultimately leads toward the living world surrounding us, not through uninterrupted stability, but through repeated renewal after disruption. Seen from this broader perspective, the earliest apocalypse becomes inseparable from the existence of every modern cell. The copying of life never paused long enough to disappear entirely. Across approximately 4 billion years, one generation passed its chemistry to the next, linking the earliest survivors with every leaf, every coral colony, every bird in flight, every microscopic organism, and every human being through an unbroken biological thread that still continues across Earth today. Look upward on any clear night, and the moon still carries the oldest visible chapter of Earth's story. Across its bright highlands and broad dark plains, the marks of unimaginable collisions remain preserved with extraordinary clarity. An airless surface, lacking weather, flowing water, and active plate tectonics has protected those immense scars across approximately 4 billion years. The record endures almost exactly as the bombardment left it, offering a lasting memory of an age that transformed every rocky world in the inner solar system. The familiar patterns visible during the full moon are therefore more than features of a neighboring world. The pale highlands preserve countless overlapping craters from the earliest epochs, while the darker plains formed when later volcanic lava flooded enormous impact basins. Each circular depression and sprawling basin belongs to a sequence of events that unfolded while Earth was also enduring relentless collisions. Looking toward the moon today means looking directly at surviving evidence from the era that almost prevented everything that later flourished upon this planet. Far from those lunar landscapes, another archive rests within carefully protected collections. The zircon crystals from the Jack Hills appear almost unremarkable at first glance, transparent grains scarcely larger than ordinary sand. Yet they contain the oldest known material formed on Earth, preserving chemical memories from a world whose original surface vanished billions of years ago. Those tiny crystals endured mountain building, erosion, burial, and renewal, while carrying information from a time when the young planet was still recovering from its earliest upheavals and already developing environments capable of supporting the chemistry that would eventually lead toward life. Everything reconstructed throughout this journey has emerged from surprisingly modest evidence. A few hundred kilograms of lunar rocks collected during human exploration, microscopic crystals surviving within ancient sediments, cratered surfaces preserved upon neighboring planets, sophisticated laboratory measurements, and continually improving mathematical models describing planetary motion have each contributed part of the larger picture. None alone tells the complete story. Together, they reveal a history far richer than any single discovery could have provided. That history speaks less about inevitable outcomes than about enduring possibilities. Earth's beginning was shaped by repeated disruption, changing environments, and long intervals whose details remain hidden beyond complete recovery. Even so, enough favorable conditions persisted for geology, chemistry, water, and time to remain connected across immense spans. The result was neither immediate nor guaranteed, yet continuity emerged despite extraordinary planetary instability. The young solar system repeatedly subjected Earth to collisions capable of transforming oceans, atmosphere, and crust. Those assaults never erased every environment capable of supporting continuing chemical evolution. Within deep hydrothermal systems, fractured rocks, and other protected settings, processes leading toward biology, or perhaps biology itself, continued across generations while the surface repeatedly changed above them. From those persistent beginnings, every later branch of Earth's living world eventually descended. The oldest lesson preserved within the moon, the zircons, and the rocks beneath our feet is one of uninterrupted continuity. Generation followed generation. Chemistry became biology. Biology diversified into countless forms, and every living organism inherited a place within that same unbroken sequence. The first apocalypse belongs to the distant past, yet its legacy remains present in every cell alive today. Across billions of years, the thread was never entirely broken, and its remarkable passage through time continues with every new moment on Earth.